Okay. Happy Monday. It's test week. How we feeling about that? Yeah? Okay, so some of y'all are, I don't know if that's a sarcastic thumbs up or not. But there we go. All right. So a couple of announcements to start, and then we'll finish up talking about force and velocity, and then we'll talk about why when you touch something hot, you want to pull your hand away. Okay. So was a little bit of confusion that is apparently my fault as usual. On the cognition to contraction worksheet assignment. I just reposted last year's version and I didn't bother to look at it. And apparently on there it says like this is not going to be for a grade, or you don't have to turn this in or whatever. And that is not true. And so because of that, I guess some of y'all did not do the worksheet or did not turn the worksheet in. That's okay. What we're going to do is Ty's going to open it back up, and we want you to do it and turn it in by this evening. What we will then do is we will post the correct version. Okay, we'll post the correct version. And by correct, I mean all the answers, the things that you're going to have to know for the test. Okay, so we want you guys to try, we'll look at it, and then we'll post that. So that's one. Okay, 2, Wednesday is going to be review, answer questions, but we're also going to play Jeopardy. And so with the Jeopardy, you guys can put yourselves into groups and you'll play against each other. The group that wins will get like a bonus point on the test. Okay. But you can't use your notes. You can't use the PowerPoints. You just got to show up and see how we do. Last year we let people use their notes. Nobody ever missed a question. It was kind of annoying. It made Ty and I have to write increasingly sort of, I don't know, difficult and tricky questions that we didn't really love. So we're going to see where we are. That's going to be Wednesday. Okay. Some of y'all, and there was just a couple, I don't even know if they're even here today or not. I'll reply to the emails. A couple of people asked if we could maybe move the test to Monday, or if you individually could take the test on Monday. And because there's 85 people in class and I just had a couple, we're leaving the test on Friday. I appreciate that may not be the world's most convenient thing for everybody in your life circumstances. And I understand that, and I'm sorry, but we're gonna leave it at Friday here. Okay. We will take the test here in this classroom in person with a pencil and pieces of paper. Okay. You don't have to have a lockdown browser. You're not using your laptop or anything else. We're doing this old school. Okay. We're doing this old school. All right. Any questions about that?
TV, are we able to come 30 minutes early like last semester?
Oh, yeah. So, I assume you get here. Doesn't seem to be anybody in this room before us. I will do my dead level best, depending upon how Ellis does in the morning, to be here at about 8:30. Okay. If you want to come and start the test at 8:30, you may do so. Okay. You can come, you can start. We'll have you guys sit down here in the front. You can fill yourself in and work your way backwards. If you want to get here at 8:30 and ask questions and continue to study, you just sit in the back, you keep your stuff open, but we'll give you guys a little bit of extra time. If you'd like to do it. Okay. Thank you, Ty. All right. Any questions? Going once, going twice? Yes, no, maybe. All right. So we finished on Friday doing things like this. So here's what the fun part with the name tags. Ariana, do you remember from Friday when we go fast, what happens to our ability to produce force? There's less. Very good. Perfect. Yeah. Okay. there is a relationship between how fast you contract a muscle and how much force you get. And during concentric contraction, so a shortening contraction, curling something up, using your tricep to push something down, doing a squat on the up portion, the faster you go, the less force you can generate. Okay? So when you get really, really close to your maximum force, the weight moves, you're straining the weights going really, really slowly. Okay? That's that relationship. We'll talk about why that is in just a second. Okay? When there is no velocity, when there's no movement, I'm holding curl right here. I'm holding in the squat pose. Okay? I can generate more force there than I can when it's moving. At any joint angle, okay, no matter where I am in the range of motion, I can get more force isometrically than when I'm short. Okay? We'll take what happens in those two, and then we'll do the weird one, then we'll do the eccentric one. Okay? The reason that you get less force when you go fast, it's physics and it's cross bridge mechanics. Okay? It all goes back to the cross bridges, and it all goes back to the cross bridge cycle. In order to continue shortening and to move, okay, I have to break and then reform and break and reform the cross bridges hundreds of thousands of times. So, in order to do this and to do it quickly, the faster I go, the more I have to break the cross bridges. The more frequently I have to break the cross bridge. So the more frequently I have to let go, the less force I get at any instant in time. And to go very, very fast, at any moment in time, there's going to be a larger portion of them that are not attached. Okay? So that's why when you want to lift the heaviest possible weight in a shortening contraction, you got to go really, 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 really slow. Because then there are fewer cross bridges that are going to have to be broken at any one given point in time. Okay? Everything comes back to structure and those cross bridge mechanics that are going to impart force production. So when I do an isometric contraction and I'm just here and I'm holding, you don't ever really have to break. Okay? They will break some. Some will go on, some will break, others will get turned back on. But there's very, very few that are broken at any one given point in time. Okay? If I break more cross bridges by going fast, what happens to the amount of ATP that I have to use? It goes down. Explain.
Using fewer cross bridges, there's less ATP being used for the head copy.
Okay, I gotta think my way back through this, Soren. So if I'm using fewer, so I see where you're coming from, and it's an interesting idea, right? When I'm going as fast as I can, imagine you're going to do a sprint. Okay, I'm going to sprint. I'm trying to generate as much force as I can, but I'm also trying to go as fast as I can. So I'm efforting to use all of the muscle, but I have to break the cross bridges really fast. Okay. So where do I use the energy in the cross bridge cycle?
The ATPase cycle.
At the ATPase, but it does, I use it to do what? I promise you, this will be on the test. Brandon? Okay, no, that's great. Thank you, Lon. Brandon, were you going to say to break the cross bridge? Okay. I use energy to break the cross bridge. So when I go fast, if the reason I get less force is because they're broken more often, intuitively, what's going to happen to energy use? It's going to go up. Okay? Which you all understand just right with your daily life. If I said, hey, walk fast versus walking slow, which one feels more difficult? Right? Which one is metabolically more difficult? Running or walking? Running, of course, right? You weigh the same. You got to have more force and more speed to go, right? That's why we use more energy to go fast. That's why even if it's a lightweight, but you lift really, really quickly, you will very often fatigue at a faster rate. Okay. It's all about cross bridge. So isometrically, I'm just holding, I get more force, but I also don't have to cycle the cross bridges, so I don't use as much ATP. I use some, but I can hold this like this a little bit longer. Okay. Does that part make sense? Lane?
So fatigue is related to the amount of ATP.
It is 100% related to the amount of ATP that you use. Absolutely it is. We will spend like a whole week talking about the ins and outs of fatigue and why not having ATP matters, all of the byproducts that get generated of our ability to try to make more ATP and how that affects things at different places. But absolutely, the more energy you have to turn over, the more likely it is that you will fatigue and not be able to continue to generate force.
What is store elastic energy?
Okay. Great question. Happy that you asked. Let me explain. Okay. Now comes the weird part of all of this. Okay. Eccentric contractions. Right? Trying to pick it up and go fast, you get less force. You don't do this very often. You don't think about doing this very often. But if I said, rather than pick those backpacks up, if we said lower the backpacks down, do an eccentric contraction, this is what the relationship looks like. Okay. And as you can see, what happens as velocity goes up, what's happening to force production? It plateaus, okay? It absolutely does. In comparison to the force I get isometrically, what happens? It goes up a little bit. I get more force eccentrically than I do isometrically or concentrically. And eccentric contractions are in general considered to be independent of velocity. Their force does not depend on lengthening velocity. Okay. So that should tell us a couple of things. Okay. If we lose force as we go fast concentrically, why are we losing it? Tell me again. Why are we losing force when we go fast concentrically?
Because we have to break off.
To break the cross bridges. Very good, Todd. Okay. So if I'm not losing force as I go fast eccentrically, what can we assume isn't happening? Helen?
No cross bridge.
There are no cross bridges being broken. Very good. Okay. And no gets us in trouble. Absolutes gets us in trouble, but it's very minimal. When you do an eccentric contraction, we do not break and cycle the cross bridges nearly as often as we do concentrically. So you can go fast, but you're not having to break the cross bridges to go fast. Part of this is about an eccentric contraction is just, there is gravity, okay? The dumbbell weighs whatever it weighs. When I want to pick it up, I got to get ever so slightly more force than gravity is exerting. So I got to win, I got to beat gravity. When we lower it down, we generate ever so slightly less than what gravity is generating. We're going to let gravity win, okay? So part of it is that we're doing that, but we just lock the cross bridges in and we just let them get stretched a little bit. They hold on and then down we go, okay? So I'm not breaking cross bridges so I don't lose force. But additionally, I use fewer and I get a little bit of an increase as I go fast because as we stretch the muscle as it goes down, we store elastic energy in our connective tissue, in the ligaments, in the tendons, in the epimysium, in the paramysium, and the endomysium. Okay? It's like there's a rubber band in every muscle, and as it stretches, it's resisting against the gravity, and it's going to maintain some of that force that, again, does not have to come from cross bridges. Okay? So I get a little bit more early on as I go from really, really slow eccentrics to kind of moderate, And then after all of that, there's no change. Now, if we go really, really super fast, kind of super physiologically, you get some weird things where force really goes up because some wild things happen in the connective tissue at super high velocities. And all of that, which may, to our question from last week, in rare instances, be something that happens when we have catastrophic, like ligament and tendon injuries. So the force goes through the roof, okay? But that's what we've got. So you can lower the weight down all day long, and you're never going to get fatigue because it's metabolically doesn't cost us very much, and you can lower down way more weight than you can ever hope to pick up. It's all about the cross bridge mechanics. So that's the storing the elastic energy. This why does this happen is the eccentric side of things that's over here. Okay. Okay. So the last little bit on all of this is some physics or biomechanics. Like, what is going on? No, what happened? Why is there a what? That was weird. Okay. Is this concept of what we call power. Power is force multiplied by velocity. Okay. So in this graph, I flipped, well, here's the force and the velocity portion like we had on the previous graph on the force velocity curve, right? So high force, no velocity, higher force, slow velocity. As velocity increases, force comes down. If you take the X and Y axis and multiply them by each other, you get a curve that looks like this. This is called a power curve. Okay. So power tends to be optimized at about 1/3 of max velocity and at about 2/3 of max force. Okay. That's what this looks like. Okay. And so this power relationship, this is how we apply force and velocity in human movement. Okay. This is how we apply all of this. Multiply those two things together. So when you want to run as fast as you can, you're actually not contracting your muscles as fast as they can possibly go. You're going to generate this power, which moves your body weight. It needs to be somewhere in here. Okay. So that's how we're going to do all of this. This can be trained. You can shift this power curve a little bit. You can shift it out to a little bit of a faster velocity with some training. Okay. Here you see power curves, right? And this is at a percentage of the fiber's peak force, but this is power. So the graph is slightly different, but the relationship is what is important. Here are, this book called it a 2B. It's really, this is a 2X fiber. Here's a 2A fiber. There's a slow twitch or a type 1 fiber, right? It's going to be here. So you can see these different power curves based upon the individual muscle fiber types. If maximum power gives us sprint speed and jump height, okay, then having more type 2 fibers naturally gives us more power. Their myosin ATPase works faster. Their force per sort of muscle size is higher, so you're getting kind of a double whammy. This is the same curve, but it's 2 A's and 1 from a different kind of thing. And what they did was they did some training, and what you can see is they called this a taper, but they had sprinters and they trained them, and then they basically tapered off or they shut down some of their training, and they saw this shift up in their power curves. So they actually got more power by taking a little bit of time off from training, which makes them an even better sprinter. Okay. So all of these things fit together. All of this fits together. You have muscle size that gives us force. Of that size, you have motor unit recruitment and motor unit firing rates or action potential rates that provide the nervous system control. Then you have to lay on top of what you can do with those things. What's the joint angle? What's the moment arm at that joint? And then what's the velocity at which I want to try to move? Okay. And so all of these things work in concert together to figure out how much can you squat? It's Monday. How much can you bench? Right? How fast can you move the barbell or something if we're doing it that way? Okay. So that's how we get force. And then that's the application of force to movement. And much of it comes back to cross-bridge cycle, how actin and myosin interact with each other, and then how that cognition to contraction works so the brain can tell those cross bridges to form or not. Okay. You guys have questions about all of that? Fail.
You don't have to know like the formula and how to apply it on the test. It just
Which formula and what?
like
Power formula?
yeah.
So you need to know that power is force multiplied by velocity. Yes. And the general application that more power means more sprinting speed, higher jump height. But that's really, and that there's differences in the fiber types and that, but that's general, that's what I want you to know. It's that very basic stuff. Okay? Okay. With our time that we have left, we're going to talk about something called sensory motor integration. Okay. Sensory motor integration. So sensory system is bringing information in from our environment. Okay. Everybody put your hand flat down on the desktop. Tell me what you feel, okay? Yeah. What does the table feel like? Describe it for us. Cold. Good. Anything else?
Smooth.
Smooth. Cold. Okay. You guys agree? Okay, all of you are feeling those things, right? So we're sensing temperature. We're sensing what is the surface like, touch, what does it feel like in that way? Okay. If I do that, is that better or worse for you guys, right? You all can sense that there's light and dark or light and absence of light. That's sensory information. Okay. That's sensory information that you're bringing in. We bring in this information all the time. And when you're doing a muscle contraction, you're going to integrate all of that information, right? And you may use that information to alter your range of motion, your force production, your recruitment order, all of these other different kinds of things, okay? When you go up a step, you have a sense when you put your foot up, where's my foot in the air? Like it's up, okay, it's made contact, now do this next thing, right? If I had you come up and close your eyes and I remove visual information, things begin to change a little bit, okay? There's all kinds of fun things. We could spin you around in a circle and then ask you to look at a thing and try to throw a ball and you throw it to the wrong place because we're tricking the brain by giving it different sensory information. Okay, so we're going to kind of breeze through a lot of this. But in general, right, we've been talking about in the peripheral nervous system, this motor side of things, the somatic systems, how we're going to go down the axons, right, through the motor neurons, down the axons, out to the muscles. Okay. Well, there's also going to be sensory information as part of the peripheral, and all of this then gets sent back into the central nervous system. So we'll talk a little bit about how we get that and what happens. Okay. Here are some parts of the brain that I'm sure you guys have seen before. Okay. You probably learned it in general psych. You probably learned it in anatomy. Okay. So we're going to talk about just very, very quickly, right? The cerebrum, the diencephalon are basically the thalamus and the hypothalamus, the cerebellum, and then the brainstem. Okay. So we've got the cerebrum where we're going to have this conscious awareness of stimuli, thinking, control of movement, and all of those things. So this area sort of up here. All right. We have the diencephalon, which is the thalamus and the hypothalamus, which are going to be right in here. Okay. At the thalamus is where the sensory information that we gather is going to come back in and get integrated right there. Okay. Then the thalamus or the hypothalamus will send signals back out to other parts of the brain. We're not going to spend much time right now talking about how we maintain homeostasis at the hypothalamus, but it will sense temperature, it senses hydration status, a whole bunch of other sorts of things. Okay. We've got cerebellum here at the back. That's going to help with motor control. And then you've got the brainstem on this area down here where we have our autonomic centers, right? Some of our kind of automatically programmed types of stuff. And then certain kinds of sensory information, especially pain and our ability to have natural analgesia or our natural ability to inhibit pain is also going to partially be driven out of the brainstem. Okay. So those are the kind of main brain areas. I'm not going to show you a picture of a brain and be like, hey, what is this area? Have I hidden this thing? Have I flipped it around? I'm still scarred from when I was a biology undergrad at lab practicals and all of those things. Okay. We're not gonna do that. So if we look in the cerebrum, okay, you've got the frontal lobe here in purple. That's going to primarily be where intellect lives and exists. And this is where the primary motor cortex is. So the initiation of movement is mostly going to originate here in the frontal lobe. Okay. You've got temporal lobes over here on the sides, here in blue. That's where we're going to have auditory information that's going to be brought in. We've got parietal lobe, okay, where we're going to have sensory sort of input. And then you've got the occipital, which is going to be back here in the kind of darker blue, which is just this. If you bop yourself on the back of the head and you lose your eyesight for just a second, that's why. That's where the vision and all those neurons are. We're going to mostly focus as we kind of go forward on the interactions between parietal, where the sensory information comes in, and the frontal lobe, right? So we bring stuff in, right? It is sort of sensed and processed here, and then that may provide some signals and some influence into the frontal lobe to change how we're contracting our muscles. Okay. Okay. I know you guys have seen this. I want to make this really quick distinction between things. Okay. When we look in the peripheral nervous system, right, you don't have to know there are 12 cranial nerves. You don't have to know their locations. You don't have to know their names. I assume that you guys have already learned those. As long as they're working, we're doing fine here. But I do want to talk very briefly about sort of issues in the sensory division and issues in the motor division. And the primary thing that I want to make a distinction on is how we term or talk about basically these nerve fibers or these nervous system axons, our ability to send information either in or out. Okay. Sensory information moves from outside, right? The periphery, arms, hands, feet, things we're touching, things that we're seeing in. That information, as it goes from out to in, is sent along what we call afferent nerve fibers. You have these receptors for those. They then signal up an axon right into the spinal cord. Those are the things that go from out to in are afferent. Then we have our motor axons and our motor neurons and those things that go from the brain down the spinal cord out. Those are called efferent fibers. Okay? You guys need to know that very individual distinction. And so we are always having this interaction between afferent information being brought in, having some influence potentially on the efferent stuff going out, and then the efferent stuff going out, then if you change that, it's going to alter the stuff the afferents are picking up, and then we have this kind of constant crosstalk between those two things. Okay. All right. You guys get sensory input from basically every organ in your body. Almost all of them. Okay. You have internal organs that are going to give you sensory input, right? Every time you have a tummy ache, seems to happen a lot at the Black household, right? When you have a tummy ache, you know that you have a tummy ache because there are sensory neurons or sensory fibers and receptors in your stomach or in your small intestine that are going to let you know what's going on there. Okay? You have sensory fibers in connective tissue, especially connective tissue around bones and joints, right? That will sense stretch. and those things. You have a lot around your blood vessels because it's really important for us to be able to control blood flow. You have a ton in your skin, and different areas of the skin have more than others, right? They have more than others. And then you have sensory receptors in your muscles. It'll sense force and length and temperature and a host of other things. We typically break down what we call receptors. They're sometimes called afferent nerve fibers. They are mostly going to be what we call type 3 and type 4 afferent receptors, or 3 and 4 afferent neurons, based upon, we make distinguishes among them based upon the type of input they respond to. Okay, so everyone take your finger, poke your arm, feel that? Okay, you are activating, you feel that because you're activating what are called mechanoreceptors in your skin. If you press hard enough and deep enough, you'll activate mechanoreceptors in the muscles in your forearms. Mechanoreceptors respond to pressure and stretch. Okay, we say touch, but really touch is pressure and stretch on those kinds of things. Those are mechanoreceptors. When you sense hot and cold, you have thermoreceptors. You have ones that respond to hot stimuli, some that respond to cold. Some will go both ways and respond to both. You have what are called chemoreceptors that respond to various ions. Okay, ADP, lactate, hydrogen ions, or acidity. Okay, potassium is an especially strong. You have these chemoreceptors. You have what are called nociceptors. Okay, now I should probably put the nociceptors in a whole separate category, because within the nociceptors you have mechanoreceptors and thermoreceptors and chemoreceptors that generate pain. If you press hard enough, you go from I feel this, it is touch, to ooh, that kind of hurts, right? You go through this into this, but those are going to be those. And then the ones that we use to see light, and those things are called photoreceptors. Okay, you are constantly getting information from your external and internal environment and monitoring that via all of these afferent receptors or these afferent fibers. Okay. Okay. So from an exercise perspective, we're going to primarily focus on what's going on in the muscles and how some of this stuff gets sort of brought into the works together. I'll be really honest, we could spend an entire class, like an entire whole class, like an entire 16-week course, just talking about sensory motor integration and its role in controlling force production and a whole bunch of other things. So you guys are going to get just a little bit of the tip of the iceberg on things. Okay, so we'll start with, why do muscles and joints need sensory input? Well, we must be able to adapt force production from moment to moment. Okay, everybody stand up. Everybody stand up. Okay. All right. We're going to try a thing that's may go terribly, terribly wrong. But you're standing up, okay? Everybody stand on your left leg. Okay. Right foot down. Okay. Now switch, stand on your right leg. Okay. Back down. Watch the person in front of you. Back to the left leg. Watch what their body does. As you go up, right, you see how we lean to one side? That sensory motor integration, we know that I'm going up, my balance shifts. I got to shift what muscles are contracting in my posture. Now, up on one leg, okay? And we're a little far enough off. Very, very gently, just slightly, just nudge the person next to you on their shoulder. Okay? That was not a gentle nudge, Carla. Okay? Just ever so slightly, you're making it take a little bit more, right? Now, everybody do this. Try this. This may go bad. Okay? You're up. I want you to lean and lean and lean until you have to put your foot down. Okay? Okay, good. If I gave you something that blocked the sensory information, you might not be able to perceive that you're doing this, right? And boom, you just fall right over. So why do we need sensory information? So we don't fall down, so we don't hurt ourselves, okay? So if we're doing complicated motor tasks, we can in real time make slight adjustments or large adjustments to let us accomplish that particular task. Okay? All right, y'all can sit down. Okay? In our muscles, we're going to talk about in our joints these sort of four broad categories of receptors. You have a thing called a muscle spindle. Okay? These are specialized muscle fibers. They live in the muscle. Okay? They're going to monitor how shortened or lengthened a muscle is. It monitors the muscle length. Okay? You have things called a Golgi tendon organ that live just at right in the where the muscle all kind of comes together and the tendons begin. Right? So in my quad, I have Golgi tendon organs right here where the patella tendon begins. They sense force production. Then you have things in your joints that are called kinesthetic receptors that sense what's my joint angle, where is my arm or leg or head or whatever joint is, where is it in three-dimensional space? Okay, these are little receptors. They have fluid in them, and as you move, the fluid shifts around, and that tells us things. Anybody ever had, probably not, maybe not as an adult, but like had an ear infection or something, right? And you feel like your entire sense of like where you are in space, your balance is all off. Okay, it's partially because you have kinesthetic receptors sort of in your ear as well to help us sense things. Then we have these things that are called free nerve endings. We call these type 4 afferent fibers that are all through the muscle, your joints, your skin, and they're going to help us pick up pressure, temperature, chemical environment. Okay, we'll pick on somebody else. It's going to be in here. Hope. Have you ever done any sprints in your life?
Yes.
If you do a sprint, and I say sprint as fast as you can for as long as you can, what do your muscles begin to feel like? How would you describe what's going on in your muscles?
Very fatigued, very tired, feel like I need to stop,
Okay,
sore.
maybe sore. Is there a different sensation? Like they are fatigued, like you know that like this is telling me that it's big, but like what? Like if we describe like the table is smooth and it is cold when you're doing sprints, what might you describe the sensation from in your muscles as being?
Burning.
Okay, somebody said burning. Hope you want to
Tingling.
tingly, burning. Okay, Fernanda. Like jello. Okay. That is all information mostly from these. The burning in your muscle is from hydrogen. From the formation of lactic acid, as things become acidic, it burns. The jello is force production has gone weird, and so my kinesthetic receptors are doing strange kinds of things. Okay, so if we're getting this feedback constantly, and then you use that to make a decision. I need to stop, right? Because I can't go anymore. My muscles are very fatigued, or they're very tired, or something bad is going to happen. Okay, Zach.
All right, I have a question.
No, that's okay.
And this is like a crazy, like hypothetical question.
Okay.
If you took like some kind of drug or something that stopped the Golgi tendon organ from sensing muscle force, what would happen? Like, would you not have a limit to your force, or would you not be able to produce any force at all?
No, it would be more the first one. So if you could selectively block the Golgi tendon organ, you would, especially if you're a person that's not that well trained, you would be able to generate more force immediately. Okay. Now, might that more force then lead to tendon injuries? Yes, it could, but you should immediately be able to, as we'll see in a minute, that when the Golgi tendon senses high levels of force, its reaction is turn off that muscle, right? Its signal is turn off, if I'm squatting, turn off the quads, turn on the hamstrings, put this fucking weight down. This is too much, stop, right? So yes, you could do some of those kinds. Okay. And I'll give you guys an example of what some of this looks like in a minute. Okay. Here's a muscle spindle. A muscle spindle is a special kind of muscle fiber. It sits in the muscle belly like all of your other muscle fibers, okay? It is a collection of, they look a little bit different in the microscope. We call them mini fibers, but they're called intrafusal fibers. Regular muscle fibers are called extrafusal fibers. Could not make the least bit of difference, okay? What we have though, is you have these spindle fibers all throughout the muscle, okay? And they have both sensory and motor innervation, so they can change their length, right? But the primary thing that happens is they sit in the muscle, and especially as you do eccentric contractions, as you lengthen the muscle, then those spindle fibers get stretched, and their response to stretch is to send a signal from the muscle to the spinal cord. Synapse at the alpha motor neuron, doesn't even go back to your brain, stays in the spinal cord and tells those motor neurons that go to that muscle, hey, we need more force. We're getting lengthened out, we're getting stretched. This could be catastrophically bad. Give us more force, right? Don't lower the thing down. Make sure we want to not be able to do that. So what you think about with this is, I'm struggling, I'm trying to squat up, it's too heavy, it's pushing me down. As it starts to lengthen like that, then these get activated and they say, give us more force. Sometimes that works, okay? Sometimes that works. The best illustration of this is something called the stretch reflex or the tendon tap reflex, okay? Let me see quickly if I can do this. If I sit up here and get nice and relaxed. Okay. What I'm doing when I hit the patella tendon is the patella tendon pulls on the muscle and it lengthens those muscle fibers. The spindle fibers then signal, this is called a reflex. They signal to the spinal cord and it tells the neurons in those muscles that are being lengthened, fire, give us more force. So then I kick my leg, okay? Stop the stretch, give a shortening. That's what's happening, okay? So that's the tendon tap reflex. It's driven by muscle spindles with a sense length. Because they have this gamma motor neuron, because they have a motor innervation, as you lengthen the muscle, the spindle gets stretched, but then we have an ability to then reset the length in the muscle spindles to make them either more or less sensitive to further stretch. And so there's this very complicated kind of dynamic that goes on in there. You can train your spindles by doing some stretching and doing some other kinds of things, but it can then kind of reset this to become more or less sensitive. Because if you're doing stuff where you want to be able to lengthen, you don't want that extra force, then you can change the settings and basically kind of make them less sensitive. Or if you really, really need them to be sensitive, we can change that as well. Okay. Okay, so we've talked about this. We talked about how that goes. So this signal back into the spinal cord, the spindles synapse on the same motor neurons that go to the muscle that's being lengthened. That means it synapses on what we call the homonymous motor neurons, right? The homo abbreviation means same, so it's the same motor neurons that go to the muscles that are being stretched, right? Spindles say stretch a muscle, make that muscle contract. That's what's going on, right? They also tend to shut off or relax the antagonist muscle. So when I activate the stretch reflex in my quads, it makes my hamstrings relax, okay? It'll make the hamstrings relax. Anybody ever done PNF stretching? Proprioceptive neuromuscular facilitation stretching. You sort of contract your quad, have someone actively try to stretch your quad while you're doing it, and then they stop, and then they yank your leg up, and because it's relaxed your hamstring, you can then move your hamstring through a greater range of motion, and you can do stretching in that way. So it's this sort of make use of the way that the nervous system is wired to allow us to stretch through a greater range of motion by activating the other side, okay? Now, with Golgi tendons, they don't sense stretch, which I know seems a little backwards, right? The tendons are the things that stretch. You would think the muscle should sense the force and the tendon should sense the stretch, but it's actually the opposite. The Golgi tendon senses force. They are these little nerve endings that are woven into through the collagen fibers right at the start of the tendon. Okay. And what happens is as the force in that tendon on those collagen fibers goes up, the collagen starts to stretch and kind of squeeze, and it squeezes those nerve endings, and that lets us sense how much force we're getting. Okay. And so we activate the Golgi tendon with high levels of force, but it signals in the opposite way of the spindle. We get high force, we're worried or we need to protect from too much force means the muscle rips apart, the tendon rips apart. So when we get high forces, the idea then is these will send an inhibitory signal back to the homonymous motor neurons. So high force in my quads, activate the Golgi tendon and the patella tendon, and it says quads relax, hamstrings contract. Put that heavy weight down. This is too much. Okay. That's how this one is going to go. So when you get stretch, the compensatory mechanism is more force. Don't let it stretches. Okay. More force stretches back. Here we get high force, which can also then lead to stretch, but high force, turn it off. Okay? That's what's going to go on with all of these. You can train your Golgi tendon. If you want to train your Golgi tendon, get in the squat rack, put a big heavy weight on, unrack the weight, and just stand there. By standing there and exerting a high level of force and not ripping your muscle and your tendons in half, you basically learn to adjust down the sensitivity of the Golgi. One of the ways that resistance training leads to an increased ability to generate force is we turn the sensitivity of the Golgi tendons down, and it lets you make better use of the muscle that you have and the force that you're already capable of generating without activating this protective inhibitory mechanism. Okay. Okay. We talked about a reflex. There's a couple of other reflexes, right? There's the stretch reflex, the tendon tap, these are the same one. There's another reflex that you guys have. It's called the flexor withdrawal reflex. These are often driven by sort of type 4 afferents, so touch, pressure, or hot and cold stimuli, but you touch something hot and you flex, right? I flex at the bicep to withdraw my hand, or I step on a Lego in the middle of the night, very parenting type of thing. Maybe someday you guys will have. I step on the Lego, right? And I flex with my hamstrings to pull my foot up and away. I'm withdrawing from the stimulus. Okay. That's a reflex. You usually you flex on one side, you extend on the other. It's called the crossed extensor reflex. They usually work in concert. As you flex, you have to extend to maintain balance. So you pull with one, push with the other to try to maintain the balance. Okay. We need the reflexes because they're fast. They do not have to go to the brain. They are pre-programmed, and it costs us, even if it's just milliseconds, right? Of here to the brain, back down to make that conscious decision on, ooh, that's hot. Pull your hand away, dumbass. Right? That's what's going on with those reflexes. That's sensory motor integration at sort of its most basic. Okay. Okay. So we've done this, right? When we do coordinated movements, right? You're walking, you're running, you're rock climbing, you're riding a bike. Okay. Things that require multiple muscles in multiple places and multiple things. That's going to start in the primary motor cortex. And then we're going to have these sort of issues with the basal ganglia and the cerebellum, where we're going to begin to kind of bring things in, integrate that additional stuff, and then make small adjustments. Okay. The last couple of slides are about sympathetic and parasympathetic input. I'm not gonna ask you about that on the test. I'm not gonna ask you about sympathetic and parasympathetic. We'll cover much more of that once we get into the cardiovascular system, and we'll catch up there. Okay? Okay. That's all the material cutting off here for the test on Friday. Wednesday, we'll do review. All right, we'll answer questions. We'll do our Jeopardy game. Friday will be the test. Ty has office hours this week. I will have office hours this week. If you don't know something, please come and ask this week so we can help you. Come as a group, bring a friend, all right? Okay, bye, guys.